start. So, welcome Suzy Maddah from from a reduction of reflexive perfectly integrable and Pfaffian systems with normal clusters.
Okay, so thank you for the opportunity. And this is another part of my of the results we've obtained so far in my ongoing thesis. So they are obtained within my work with Moulay Barkatou. And here C will denote the field of complex numbers, and O will be the ring of formal power series with coefficients as shown here, and K is its fraction field. So the so-called completely integrable Pfaffian systems with normal crossings are the linear systems of partial differential equations of this form, where P to Pm are non-negative integers, and the untuple is called the Poincare ring, and the matrices have their entries lying in O. Now, the integrability conditions are as follows, and what we call normal crossings, or we say that they have normal crossings to illustrate the fact that the first subsystem has is singular at points where x1 is 0, the second at points where x2 equal to 0, etc. And so what we are interested in is to, as usual for other systems, to give a complete algorithm for the computation of a fundamental matrix of formal solutions. So in the first part of my talk, I will show how these systems can be viewed as a generalization of linear ordinary differential equations, which were shown in the talk of Moulay. And in the second part, I will show how we can compute a certain a major part in a formal fundamental matrix of solutions from some associated ordinary differential systems. This will be for the general case of variables, and then in the third part I will restrict the number of variables to 2, and I will show how we can construct all of formal fundamental matrix. And so for the first part, let V be a k-vector space of dimension n. We associate to the system a set of differential operators acting on V. So I reformulate my systems in this way so that you can see that for m greater than 1, that is the case of more than one variable, the systems can be rewritten in these operators, and the integrability conditions are translated to the pairwise computation of the operators. Now for the case of one variable, we will get the linear ordinary differential system of this form. Now, there exists a change of basis such that under additional ramifications for some natural integers Si, this system can be brought into a triangular form. And the more interesting part is that these matrices have their entries as polynomials in only one variables. Now, this is an analogous result to that mentioned yesterday by Professor Laban, that if we have a set of commuting matrices, then we can triangularize them simultaneously. So this is an analogous result to that. And moreover, these AIs here have an explicitly prescribed form very close to the Jordan canonical form that we have for linear operators. And this form allows us to read the solution as follows. Now, as mentioned by Moulay, for ordinary differential equations, a fundamental matrix of formal solutions can be written as follows. And for the general case of m variables for our systems, it will have this form. This is a result by Essen and Van den Essen and Level in 1982, and also obtained by Gerard and Charrier in 1981. So here phi is an invertible meromorphic series, and the Qi, each Qi is a diagonal matrix containing polynomials, and it will be called the exponential polynomial matrix within this talk. So when I say computing exponential polynomial matrices in my second part, my interest will be to compute these QIs. Now lambda i's are constant matrices computing with QI. So as I said, what we are interested in is to construct these solutions. And so we are basically interested in formal reduction. That is the algorithmic procedure that computes that transformation, which takes the system into its triangular form so that formal solutions can be constructed. Because we know that T exists, and we know that the S exists, but we do not know how to compute them. So this is the interest of this talk. Now for the case of, for the univariate case, as you've seen with Molay, that it has been studied extensively, and algorithms for related problems are given by different authors, leading to the package we solved in Maple by Barcato and Foucher. Whereas for the linear partial differential systems, for the linear partial differential equations, there are some results. I mentioned works of Sternfels, Takayama, and Aroka Kano, Verhoeven. For the linear systems, which I'm interested in, there is the work in the 70s and 80s of Charrière, Girard, Delaine, Level, etc. And the first step of formal reduction was set in an article by Barcato and Leroux in 2006, where they perform rank reduction. I will talk more about it in the third part of my talk. And in the PhD thesis of Leroux, he shows how to construct solutions of regular systems. Also, the closed form solutions of integrable connections are studied by Barcato, Clouseau, Rasha, and Veil in 2012. So, to recall the kind of transformations that we perform in the univariate case, we perform linear transformations of this form, which takes the system into another system where A hat and A are related as shown. Another kind of transformation we perform is the exponential transformation within the formal reduction, and the effect of this transformation is on the leading term of AX. It shifts it, this should be a 0 minus alpha IN. And we do some ramifications. So one approach would be to take each of these transformations and study its effect, or study how we can perform it over a multivariate field. However, the difficulties that arise, in addition to the computations over multivariate fields, the main difficulty is that one transformation of one subsystem will alter all the other subsystems. I recall here the notation so that you can see that more clearly. So we have this set of operators, and if we take a change of basis, this will give rise, as we said, to another set of operators where the matrix presentations of both operators are related as follows. And you can see if we alter, so if we want to perform some transformation on one of the subsystems, all of the subsystems will be altered. I illustrate this by an example. So this is an example from the paper of Barcato and Leroux in 2006, where they illustrate the difficulties in rank reduction. And in rank reduction, what we try to do is to drop the rank of the singularity, which is here 4 in X, to the minimal integer value. And so if we naively apply some rank reduction algorithm, which we have in the univariate case, we obtain this transformation. If we apply it for the system, you can see here that the first subsystem, in the first subsystem, the rank in X dropped from 4 to 1, but we altered the normal crossings because now we have a singularity in Y as well. Moreover, the singularity's rank in the second subsystem increased from 2 to 3. And so this is the main difficulty. We have to make sure when we apply a transformation to one of the subsystems that it does not alter in a bad manner, in some sense, the other subsystems. And so we chose another approach. And in our approach, we try first to compute this exponential part, and in this approach we look at what we call the associated ordinary differential systems to these PDE systems, and we try to retrieve as much information as we can about the solutions from these ordinary differential systems. So given again our system, I recall the notation. If in the first subsystem we take x2 till xm equal to 0 and we leave x1, and then in the second we take x1 and x3 till xm equal to 0, we set them equal to 0 and we leave x2, etc., what we will get is this set of associated ordinary differential systems. And so each of these systems has a fundamental matrix of formal solutions where, and therein there is a Q, the polynomial matrix and the exponential part Q. And the main result that we have is that the exponential polynomial matrices Q1 to Qm of the linear partial differential system are equal to the exponential polynomial matrices obtained from each of these ordinary differential systems associated to the individual subsystems. I illustrate this by an example. So here's an example in dimension n equal 4. Here for simplicity, I give an example in 2 variables, however it works for any number of variables. So here I set x1 equal x, x2 equal y, again for the simplicity of notations. And so this is the first subsystem. If we set y equal to 0 here, and in the second subsystem, if we set x equal to 0, our set of ordinary differential associated systems we will have is as follows. And so if you compute the exponential polynomial matrix for each of these subsystems via ESOLVE, we will get Q1 as follows and Q2 as follows. And these will be the exponential polynomial matrices in a formal fundamental matrix of solutions for the linear partial differential systems. And these QIs are very important because they, if the QIs are not equal to 0, are not null for some, well, this is a 0 matrix, of course, then the origin is called an irregular singular point of the system. And in this case, the elements of the QIs determine the main asymptotic behavior of actual solutions as xi tends to 0 in sectors of sufficiently small angular opening. Otherwise, the origin is called a regular singular point of the system. And in this case, these ramifications are always equal to 1, these SIs. And the formal series converges whenever the series for AIX does. So, computing these QIs will reduce the problem of constructing a fundamental matrix of formal solutions to constructing a basis for the space of regular solutions. And so to proceed, after this example, I will give the proof or an outline of the proof. Our proof is based on the fact that there exists a natural integer s and a change of basis such that if we do a ramification only in the first variable by applying this or performing this linear transformation, what we get is a new equivalent system where the first subsystem is triangular as well as the others, but the others are independent of x1, or which is t in this case. And so we use these properties and some relations of equivalence and how the variables are related to prove our theorem. So in the second part of this talk, I will show how for the bivariate case, for the system of 2 variables, we can construct the other so-called regular part of the solution. Because now we have the exponential part, so one component that we need to construct the regular part is rank reduction. What is rank reduction? Again, I recall our notations. So given these systems, the set of Pfaffian systems with normal crossings, a change of basis will take these systems to the set of equivalent systems as follows, with these relations. And what we call the true Poincaré rank is the minimal p-tilde, which can be obtained upon all the performing all the possible change of basis, such that the p-tilde i's are simultaneously and individually the smallest possible. This is called the true Poincaré rank of the system. And what we have is that the regularity of a system of a partial differential equation of one of the subsystems is equivalent to the regularity of the individual systems. So in other words, the system is regular singular if it is equivalent to a system where the p-tildes are all equal to 0. Otherwise, it is irregular singular. And as a corollary of our theorem, we can also see that not only in the case p-tilde, each p-tilde is equal to 0, we will get a regular system. However, the true Poincaré rank of the system of PDEs is always equal to the set of the true Poincaré ranks of each of the individual associated ordinary differential equations, not only in the case when the p-tildes are equal to 0. So this can be a corollary of our theorem. However, there still remains the problem of computing this transformation, which will take us from a system with a Poincaré rank to a system with a true Poincaré rank. I mentioned that in the work of 2006 of Barcato and Leroux, they perform some kind of rank reduction, which is a generalization of Leval's algorithm for the univariate case. However, in our work here, we generalize the Moser-based reduction, and in particular, we generalize the algorithm given by Barcato in '95 to such systems because it is a prerequisite in the process of the kind of, or in our approach for formal reduction. Because not only it drops the Poincaré rank, but also it minimizes the rank of the leading coefficient matrix. If you've seen my talk yesterday, I've illustrated the importance of this. And so our theorem states that given the following bivariate system, here for simplicity, I write x for x1, y for x2, a for a1, and b for a2. So given this bivariate system, a necessary and sufficient condition for A to the system to be Moser reducible, that is for the existence of a transformation T such that the new system has a Poincaré rank which is smaller, or a rank of the coefficient matrix which is smaller, is that this polynomial vanishes identically in lambda. Now this is a generalization of a theorem by Moser for 1960 for the univariate systems for m equal 1. What is essential in our theorem is that this transformation can always be chosen as a product of unimodular transformations, and so if we perform them on one system, they will not raise the singularities rank of other systems because they are unimodular, so they are invertible in the ring. And it is a product of these transformations and polynomial transformations of this diagonal form. This does not show because this is it. But anyways, this is to say that some polynomial transformations of this form. And the reason why this theorem is not a direct result of the theorem I showed yesterday for the perturbed systems, because although the perturbed systems are in some sense bivariate systems, however, this alteration I talked about, that when we apply a transformation to one of the subsystems, we do not want it to alter the rank of the singularity in the other, requires additional structure on the system so that the transformation is a good transformation. So I'll talk more about this in my presentation at the Colchin seminar. Again, I repeat the announcement at 11 o'clock. Okay, so if you are interested of this, in this, I'll talk more about it. I give here an example, and I'll show in this example how to construct how to construct fully a formal fundamental matrix of solutions in the bivariate case. So given this example, it has dimension 2 by 2, but it can be any dimension, but it should be only of 2 variables. Now, as we said, we can compute the exponential part from the ordinary differential systems associated to this system. And if we take, again, if we take y equal to 0 here and x equal to 0 here, this already equal to 0. So we'll get these ordinary differential systems if we compute q1 for this and q2 for this. So we will get q1 and q2 as follows, and now we will have to compute lambda 1, lambda 2, and phi. So if we perform these exponential transformations, we will get a regular system. Regular system, that is, we know that there exists a transformation which can take this system into a system whose Poincare rank here is, well, p is 0 because this is p plus 1, and here it is also 0 because this is, again, q plus 1. So by our Moser-based reduction, we compute this transformation, which will take us to this system. Now that this system is regular, that is, the Poincare rank in both is equal to 0, we can use the result and the PhD thesis of Leroux, which are based on work of Level and others, to compute the other parts. So lambda 1 is given by this, and lambda 2 we can compute it, and we see that it is given by this matrix, and T1 and T2 are the product of the transformations that we've performed. So this will be a fundamental matrix of formal solutions for this system. Now this is a simple case. In the general case, it is more complicated, but I illustrated by a simple example. And so what we have for now is that for any number of variables, we can compute the exponential polynomial matrices from associated systems of ordinary differential equations. And of course, this reduces the computations to from multivariate fields to univariate fields. And we can retrieve information about formal invariants, like the 2 Poincare rank, from the matrices, from also the associated system of ordinary differential equations. The problem is reduced for any number of variables to the computation of a basis for a space of regular solutions. In the case of 2 variables, this problem, the third problem, is solved, and we can compute a fundamental matrix of formal solutions, as I showed in the example. For further investigations, well, it is obvious that what is left is to try to generalize this to, or try to solve the third problem for any number of variables. So these are some references, and I thank your attention. And of course, you can find the implementations on my website.
Questions? Okay, so I guess the questions will be asked informally after the research. But thank you very much.
Thank you.